Okay, I might go from 1 to m. What are you actually doing here? What is that operation over there? You're doing the kind of Fourier synthesis. And where do you see this kind of thing? You see that in antenna array theory. If you have an antenna array, if you want to calculate the array pattern, you do this kind of operation. You multiply e to the I k dot rho with the sources, the amplitude of the sources. Okay, in array antenna synthesis, you will do a lot of this thing. So this operation now is replaced by this operation. This operation is the same as finding the radiation patterns of these sources, instead of finding the multiple moments that come out of this. Before that, we multiply by that. This actually calculates the multiple that are emanating from this group of sources. Now, this is replaced with something that is the same as calculating the radiation pattern of these sources. Okay? Again, the same as before. The larger these sources are compared to wavelength, the richer the radiation pattern, and the more points that you need. Okay? So P, the number of points that you need to sample this pattern correctly, is also proportional to KD. So this argument still holds true. The first stage is m squared. The second stage, instead of m squared, becomes m. Okay? So the total cost becomes 2pm plus m, which is actually p, right? Is it p? 2pm plus p instead of m squared. The second stage is a lot cheaper. Then we can argue that P is equal to let me see. Okay, I'm missing something here. I have to do this aggregation ng times. I have to do it for every group, right? And then the second part, I have to do it between all the groups. I have to do ng squared times, right? The last part, I have to do it with ng times, because I have to calculate all the interactions between them. So there should be an ng multiplied the first action, ng squared multiplied by the second action, ng multiplied by the third action. Because I have to do it for every one of the group. When I translate, I have to translate between them. The ng squared group to translate between. Okay, so the total cost is actually this times ng squared. Okay, that is the total cost. This is the cost. Total cost is equal to that. But ng is equal to n divided by m. Okay, so it's 2n p. N divided by m is ng. Okay, look at the number of groups I have. It's n divided by n, and this is ng squared. So it is n squared over m squared. But n and m are linearly proportional to each other. N and m are linearly proportional. No, n and p are linearly proportional to each other. So this is actually 2nm plus p and m are the same, plus n squared over m. This is the total cost. So the total cost is that. But if I'm clever enough to pick n to be square root of n, and pick n to be square root of n, then the cost is, if this is square root of n, this is square root of n, this cost is n to the 1.5. Right? N to the 1.5, you could pick n to the square root of n. And then I have reduced the cost from n squared if I do the direct naive calculation. If I do this other ways, I cannot still escape from the fact that the total cost is m squared times ng over m squared. Okay, I have to multiply this by ng over m squared. Sorry, n over m squared. And finally, I still get n squared if I use the undiagonalized form. If I use a diagonalized form, I can reduce the cost to n to the 1.5. Okay. Are there any questions? It's rather complicated, right? Quite complicated. Yes? So this is a two-level algorithm. This is what we call a two-level algorithm. We aggregate, translate is aggregate. Okay. To get n log n, you have to do multi-level. So what happens is that the simple picture that you can draw for this is that this is a group of sources, this is a group of sources over here. In this kind of thing, you aggregate everything about the group center, and then you aggregate everything about the group center. Okay? And then you translate between group centers. It's one way to look at it. You have all the translation between group centers. And this is just two level. Okay? And if you draw it as a tree structure, it will look something like this. You have a group of sources over here. You aggregate everything to a group center in a tree structure fashion. And then you translate between the three centers, the group centers. Okay? And in order to get n log n, you have to further divide it into multi-level. Okay? So what you do then is that you try to aggregate with very small groups. Start to aggregate with very small groups. And then you aggregate them in this manner, in the multi-level fashion. And then you aggregate them into larger group centers. And then finally, the group centers that you have is very small. If you do a multi-level version, you can further reduce this cost to n log n. Okay. It's rather difficult to show you what the multi-level fashion of version is, but essentially this is the multi-level fast multipole algorithm. Okay, this is the multi-level fast multipole algorithm, and you can think of this aggregation as being a way to finding the radiation pattern of an array of sources. Say the aggregation part is just this part. Say if I have a group of sources in a box, many of them, millions of them, maybe. Okay, I want to find the radiation pattern of this group of sources. What can I do, and what clever method do I have to my disposal? I can divide this group of sources into smaller groups. Okay, I can start to aggregate the groups of sources inside this box first, and form the radiation pattern about this group, and then I do every similar thing to every of the groups within each boxes. And then after having found the radiation pattern of each of the groups inside the box, then collect, say, 4 boxes, and then translate the radiation pattern to this group center. Okay, I can do a very simple translation using this very simple operation. This is a scalar operation. I can do a shift very quickly. Then I find the radiation pattern of the sources in the larger box. I do likewise to this group. Okay, I find the radiation pattern of the group of sources in these larger boxes, and then do a translation to a bigger one, the center of this larger box. And finally, I do a translation to this big center. And then if I'm out here, I will observe the radiation pattern of all the sources inside this group. But I can find this radiation pattern in n log n operations. Okay, n log n. So you can think of the multi-level fast multipole algorithm as also another way to find radiation patterns of sources distributed non-uniformly in n log n operations if you were to use the multi-level version.
Isn't that what mesh generator does in the simulator?
Mesh generator does not provide you with the complexity. Say if you have a group of sources, it looks like that. If I want to find its radiation pattern, how can I find it? The n source points here. How can I find its radiation pattern in order n log n? How can I do that? I can use Fourier transform technique, but it doesn't work efficiently here. If I use multi-level fast multipole, I can find its radiation pattern in order n log n by multi-level aggregation. Okay? So it's different. Mesh generators don't give you that complexity. Mesh generator does not give you the radiation pattern as well. The difference here is that these points are non-uniformly distributed in space. Okay? You can find its Fourier transform. Radiation patterns are just Fourier transform. You can find its radiation pattern by doing a Fourier transform of all the source points within this box, but there will be a lot of zero padding involved, so this Fourier transform becomes inefficient. But multi-level fast multipole will find you the radiation pattern in an efficient way in n log n complexity without zero padding. Okay, and you essentially do this kind of thing. Okay. Well, it's a rather complicated subject, but I hope that you get it. And if you have any questions so far, if you have any questions that you'd like to ask.
That's the limit to n log n.
What is that?
The limit is n log n.
Right, right.
Is that like related to entropy or something? Or,
Like the what? Radiative transfer theory?
related to entropy or like the limit?
No. The analysis is rather simple. The analysis is that if you organize things into trees, say if you have n unknowns, okay, n unknowns over here, you have to organize things into, say, octree. In this case, the quad tree fashion. In order to exhaust the tree, okay, you can easily show that the number of levels to reach the top is log n. Log n. And there are n sources that you have to deal with. So the work is order n in the first stage. You can also show that the workload is order n on the second level, order n in the third level. Because even though they are lens boxes to aggregate, but those radiation pattern gets richer. So if you have this box, its radiation pattern might look very benign. But if you go to a larger box, its radiation pattern will become richer. If you go to a bigger box, the radiation pattern becomes even richer. What is the physics here? What causes the radiation pattern to become richer and richer as the box size gets larger? Kurt, you know?
Grading loads.
Grading load and antenna array theory, right? Essentially, it's the physics of interference. These sources have chances to interfere with each other when they are spaced far apart, whereas these sources do not have a chance to interfere with each other. So as you go up the level, you have to keep more and more points to capture the radiation pattern. So even though the number of nodes diminishes, the workload remains the same. Order n here, order n here, order n here, order n here. Finally, the workload is n times the number of levels, n log n. Okay, and finding the radiation pattern. But then there's this aggregation part, which is very complicated. I'll send you the lecture notes to read on them if you want to read them.